All right, we're going to talk about camshafts. You know, the camshaft is the single most important thing in the engine. I mean, it dictates where the RPM range of the motor is going to run at, like as far as pulling from the bottom end or pulling on the top end. It dictates manifold vacuum. It dictates how it's going to idle. I mean, everything about the motor is dictated by the camshaft. It's kind of like having a computer. You know, you can have the biggest, baddest computer there is. I mean, the biggest hard drive, the fastest processor and everything. But if you got software that's not up to snuff, it makes the whole computer not up to snuff. Same thing with an engine. I mean, you can have the best of everything, the best pistons, the best rods, the best crank, biggest flowing heads. I mean, you name it, it's in there. That's fine. But if the camshaft isn't up to snuff, the whole motor's not going to be up to snuff. And that's not good. All right, let's talk about the different parts of the cam and the different types of cams there are. This right here is your typical flat tappet cam. It's what you'd find in pretty much any factory motor. The different parts of the cam are, these are the bearing journals right here. This is where it rides inside the block against the cam bearings pressed in the block. This right here, of course, is the distributor drive gear, and it also drives the oil pump. These right here are the lobes, and of course there's 2 lobes per cylinder, because I mean you have an intake valve and you have an exhaust valve, so there's 2 per cylinder. And of course what rides against the lobe is a lifter, and then from then up is the push rod, which activates the rocker arm, which then pushes the valve down. That's typical of all camshafts. This one right here is a roller cam. We'll get into lifters in a minute, what that means. But you can see the lobes look a lot different than the lobes of a flat tappet cam. That's just because these are more aggressive. These open the valve a lot sooner and they close it a lot faster than a typical flat tappet cam. This is the same thing right here. It's also a roller cam, but it's a solid roller cam. It's made out of a little bit different material. And you can see this right here, the diameter between this area right here compared to this cam right here is a lot smaller. It's because this cam right here is designed for strokers, such as like a Chevy 383, where the crankshaft stroke is increased. The connecting rods come very close to the camshaft. In fact, so close they'll actually touch a couple of the lobes on the camshaft. So the way we get around that, there's 2 ways. You can either grind the bolt face of the connecting rod, or you can simply go with a smaller diameter camshaft. And that's what we choose to do here. Rather than grind on a perfectly good rod, we'd rather just use a little smaller diameter camshaft. This right here is another solid roller camshaft. This is a billet camshaft. You can see it's got a different color. It's made out of 1 solid ingot of billet. These right here require special attention. Again, it's got the same parts as anything else, but if you look how big these lobes are compared to these right here, this is a very aggressive camshaft. This is, you know, for big lifts, like this right here is probably a 700-inch lift cam, which means it lifts the valve off the seat almost 3/4 of an inch, 700 thousandths, where a typical stock cam lifts at about 320 thousandths. A high-performance cam might lift it a 1/2 inch off the valve seat. That's a 500 lift cam. Well, this one here being 700 is almost takes the valve 3/4 of an inch off the valve seat. That's a long way. The thing you need to remember about billet camshafts is mainly the distributor gear right here, the distributor drive. Most cams just use an iron gear or a steel gear. These are your typical gears that would normally come with or go with any other type of camshaft. They ride against here. Like I say, they drive the oil pump and they drive the distributor. Nothing fancy about these. Chevrolets are a lot bigger than a Ford, as you can see the size right here. Okay, but a billet cam you have to be careful with. They run a bronze gear. And the reason you run a bronze gear, if you run an iron gear on one of these or a steel gear, it'll just eat the teeth up on the drive, on the cam drive. And what you'll end up with is something that looks like this. That's not good. Once that happens, it's catastrophe. I mean, all the metal from here has just gone down to the rest of the motor. This is typical when you don't change distributor gears or you use an old worn out gear on a new camshaft, anything like that. You're going to lose this gear. So on billet cams, you want to go ahead and use a bronze gear. If you don't match those, even with a flat tappet cam, if you put a steel gear on a flat tappet cam where it's supposed to have an iron gear, the same thing will happen. So you have to be careful with that stuff. All right, while we're on the subject of distributor gears and cam gears, let me show you a little something here. These are 2 typical gears. This one's of a small block Chevy, this one's of a small block Ford. A lot of you probably know to run high volume oil pumps in performance motors, and that's fine and dandy on most Chevrolets. On Fords though, it's something that you might want to think twice about. What drives the oil pump is the distributor gear. And as you can see on the Chevrolet gear right here, this one, the teeth are a lot larger than the Ford gear. This is the Ford gear. This gear, being that it's bigger, takes a bigger load. The Ford gears, what's real common to happen is with high volume oil pumps, it just wipes the teeth off, especially if you're running a thicker oil, like a straight 30 weight or a straight 40 weight or something like that. Even in situations where you're not doing that, it's not uncommon to wipe the teeth off of a Ford distributor gear just because the load of the oil pump is so great. So you want to watch that kind of stuff. Another thing is when you're running bronze gears, there is a drawback to running bronze gears. This stuff is soft. It doesn't last very long. So if you're going to run a solid roller cam on the street and you're going to run a bronze distributor gear, you got to check it every now and then because these are soft. They will wear out. Now some manufacturers have taken it upon themselves to use a different type of material on the cam gear right here. Some are usable with a steel gear, just like what a factory roller car would come with, like a late model Chevrolet or a late model Ford. They have a factory roller cam in them, and they use a steel distributor gear. Some cams are compatible with steel gears. So when you're selecting camshafts and going to make a purchase, you might want to check into that first so you don't end up with the dilemma of checking the bronze gear all the time. All right, what I have here is a fuel pump push rod. You know, normally this wouldn't be an issue, but on roller cams, you want to be sure you use the correct push rod. This one right here has a bronze tip on it. And just like having to use a bronze distributor gear on a billet roller camshaft, you need to use a push rod like this that has a bronze tip with a billet roller camshaft. Otherwise, you will damage the camshaft. So make sure when you're selecting the right cam, you select the right fuel pump push rod if you're going to use a mechanical fuel pump. If you're going to use an electric fuel pump, it doesn't really matter because this won't be in the motor anyway. All right, we're going to talk about one last type of cam here, the 3/4 cam. I'm sure many of you have heard that term before, 3/4 cam. And what the hell does it mean? I don't really know. Does it mean you race 3 of the 4 weeks out of a month, or what does that mean? I mean, if it's a 5-week month and you race 4 weeks, does that make it like a 15/16 cam, or how does that work? In my terms, a 3/4 cam is this right here. This is a 3/4 cam. It's missing 4 lobes. For about 20 bucks more, you can buy a whole cam. Guys in the know don't use the term 3/4 cam. That's like old school. Let's not use that kind of terminology. You either have a hot cam or a race cam or a street cam or whatever you want to call it, but the term 3/4 cam, that's pretty outdated. All right, what we have here is an assortment of lifters. I'm going to take you through all the different types and styles of lifters there are. This one on the end right here, this is your typical hydraulic flat tappet lifter. And what they mean by flat tappet is at the bottom here is flat. These are typically in every factory car there is out there from the 40s on up, if not back before that. What hydraulic means is inside here there's a plunger and there's some pretty intricate valving inside here that collects oil, and as we know, fluid doesn't compress. So when the oil gets inside here, it fills up and acts like a solid barrier for the lifter to push the push rod up. Basically, hydraulic lifters just means it uses fluid inside, where this one right here is a solid lifter. Looks identical to the hydraulic. It's also a flat tappet. The difference is there is no valving or springs or anything like that inside here. It's just a little oil area, so oil can enter the hole here through the oil galleries in the block. And when the cam lobe pushes up on the lifter, it squirts oil up the push rod to oil the top end of the motor. But there is no valving. I mean, it just bottoms out on the plunger in here to a solid bar of steel inside there. But that's a solid lifter cam. Remember the difference between a hydraulic lifter and a solid lifter. Hydraulic lifters, and we talked about lash before, and lash is the area, I'll show you right here, the area where the rocker arm rides on the valve tip. Hydraulic lifters use a zero lash, which means there's always tension between the rocker arm and the tip of the valve. Where solid cams have a little bit of space right here, what we call lash. It could be whatever the cam manufacturer wants for that particular cam profile. Usually it's 18 to 22 thousandths, sometimes 24, 26 thousandths, but either way, solid lifter cams, they have a little bit of a lash right there, and that's the tapping sound you get with the solid lifters. But that's pretty much the difference between these right here. All right, we just talked about the flat tappet lifters. You know, there is one more type of flat tappet lifter I'd like to tell you about. It's a hydraulic also. You probably heard the term fast bleed lifter. That's the typical hydraulic lifter, just like this one right here, flat tappet. But what it means on fast bleeds, basically, is that the inside valving has looser tolerances. So what it does, it bleeds off oil faster. It needs more oil pressure to maintain the fluid control inside. What they're designed for, basically, and what the advertising claims on them is that you can run a bigger camshaft and it'll idle smoother and be less radical at lower RPM. And that's basically because the lifter's not functioning properly. I mean, it's just bleeding off oil. Really, I mean, if you're going to do a performance motor right and you have a particular cam that works with the motor, get the right lifters for it. We don't recommend running fast bleed lifters in any motors that we build, that's for sure. Let's move on here to roller lifters. These are hydraulic roller lifters right here. This is what you'd find in any typical General Motors or Ford style motor of the late model years these days. And they are a roller lifter. They do have wheels at the bottom to ride over the lobes. It takes the friction off the camshaft for wear or anything like that. The problem with these are, they're fine for factory stuff, for factory applications. The problem with these, though, they're really heavy. This is a pretty solid chunk of iron here. They do have the same valving inside as any hydraulic lifter for the oil to fill up. But the problem is they are really heavy, and they use these heavy, thick retainers on top. And you might think, well, what's that have to do with anything? The problem with weight in lifters is that you need more valve spring to keep the lifters in contact with the camshaft, especially in higher RPMs like a performance application. You really need heavy valve springs. Otherwise, these things, you get valve float. Let me kind of explain what I'm talking about here. We'll take a lifter over here to this cam. You always need contact between the lifter and the lobes of the camshaft. If you don't have enough spring pressure, what will happen is it won't stay in contact. So as it comes off the top of the lobe, and in high RPM, it'll actually skip off and then come back down and make contact. That skipping area right there with not enough spring pressure is valve float, and really bad things happen in valve float. So you really need higher spring pressures with heavier weighted materials. Otherwise, it won't keep it in contact with the camshaft. The problem with higher spring pressures, you don't want to get too much spring pressure because you're just beating the crap out of the valve train, and you really don't want to do that either. Everything needs to be matched together. So as far as factory applications and lower RPMs, these hydraulic rollers are fine. But if you're going to use performance stuff, you really don't want to use those. You want to go to these right here. These look large, but they're not. They're actually hollow inside here. There's not much inside here. It's only this area down here that has anything. The reason they are so tall is to clear most lifter bosses inside the blocks. But they are very lightweight. They have a lightweight transfer bar right here. And the reason roller lifters have transfer bars, this is something you need to understand. Flat tappets don't ride on the center of the camshaft lobe. They ride on the edge, on the side right here, about like so. That way, every time the camshaft makes a rotation, it rotates the lifter also. So it's always on a fresh new surface, and it keeps the lifter rotating. They're kind of omnidirectional. They just kind of rotate on every rotation of the camshaft. And that's fine. Roller lifters can't. They're highly directional. They have to stay in line, because if these things turn, the wheel faces the wrong way and they'll tear the lobe right off the camshaft. So they have to be aligned at all times in line with the lobe as they go across. And that's what the transfer bars do, or the locating bars here. And again, the factory ones are very heavy. These are very lightweight. It's just a thin piece of steel, and it keeps the lifters in line with the camshaft at all times. Let's go to this one right here. This is a solid lifter, or solid roller lifters. They're really light. This whole pack right here is less weight than one of these right here. This entire pair is lighter than this. This is for really high horsepower, high revving applications. And again, we talked about lightweight. That means, even with big spring pressures and extreme RPMs, these won't get valve float. They're less apt to get valve float just because they're lighter. Again, they're rollers, but these are a solid, just like the first solid lifter. In fact, there's not even a plunger inside. If we can get down inside there, there's not even a plunger in there. It's just a solid base. These would allow lash. You'd have to have lash at the valve for these, whatever the camshaft manufacturer recommends. But these are extremely lightweight, good for really high horsepower and high revving applications. This right here is the lightest weight lifter on the planet. It's made out of aluminum. Actually, I'm just kidding. It's for my keychain. It's not really a real lifter at all. Let me get into another aspect of lifters here. Some people fire their cars up in the morning and they have ticking, and ticking's not bad in the morning. What happens overnight is, as you have a hydraulic lifter sitting against the camshaft, and some cylinders, the valves are going to be open and the spring pressure is pushing down. Well, what it's doing is it's pushing on this plunger here. Okay, and on a performance motor, you got a lot of spring pressure. I mean, some are double springs, some are triples. Most of them are big singles or double springs. You might have anywhere from 150 to 350 pounds of pressure pushing on this lifter. So when you shut your engine off overnight and you come back in the morning, what's happened is the pressure pushing on that plunger has bled a little oil out of the filler valve here. And which means that the lifter is now minus a little bit of oil. So when you start it up in the morning, the oil pump has to pick up oil, run it through the whole motor, run it down the oil galleries and actually fill this back up. And in the meantime, because that isn't full of oil, you're going to have a little ticking because you're going to have a little added lash at the valves. Even though hydraulic lifters don't have lash, you're still going to have some at the valve until this fills back up with oil. That's not a bad thing. A lot of performance motors get ticking in the morning when you first fire it up. It's no big deal. Don't panic over that. It's quite common. All right, there's something else that's very important you need to know here. You know, a lot of you are probably going to upgrade your camshafts in your cars for a little more performance. Anytime you do that, you must replace the lifters. If you don't, you're going to end up with a flat cam. What we're talking about a flat cam is wiping the lobes right off. I mean, you just wear them right off, so there's no lobe anymore. If you're just taking your camshaft out and you're going to put it back in, like you're just freshening up the motor or something, and you want to reuse your older lifters, you can make a simple arrangement tray like this. It's just a piece of wood with some holes drilled in it. Of course, you want to clean it. You don't want particles of wood in your lifters. But just mark the end of it right here for front of the motor. And as the lifters come out from the front of the motor onto the back, you can put them in here. And the reason you want to do this is if you take this lifter right here and you put it on the front lobe, or you swap any one of these out, it will wipe the camshaft out, guaranteed. So each lifter is an individually wearing part to each lobe. And you've got 16 different lobes on a V8 and 16 different lifters. This is very important. I mean, if you swap any one of these out, you will have camshaft failure, no doubt about it. So anytime you're doing that, if you're going to replace a new cam, replace new lifters. If you're going to just take your camshaft out to clean the motor or something and you're going to want to reuse your lifters, then just make a quick little arranger like this so you can put them exactly in the same place in the motor where you started from originally. You know, I get this question a lot, you know, how high will a hydraulic flat tappet cam rev? And when do you need to go to a solid cam? And why would I want to go to a roller cam or a solid cam? And these are all pretty valid questions that are kind of confusing. And mind you, I realize that heads porting and valve trains, this is a very confusing video. I mean, the whole aspect of this is pretty complicated. And it's a very mysterious area that a lot of people don't really understand about. You know, as far as hydraulic flat tappet lifters and camshafts, we're not in the dark days of yesterday. We're in today's technology, and camshafts are measured in millions of inches now. They're not, you know, they're not machined with a draw file or anything like that. I mean, it's pretty precision equipment that's doing this stuff. We've got motors out there running with hydraulic flat tappets at 7,000, 8,000 RPM consistently. With no problems. So there's a myth that, you know, hydraulic lifter cams can only go to a certain RPM. That just gets blown out the window, okay? Solid lifter cams, yeah, they can take a little bit more RPM, but you have to keep in mind that, you know, there are other factors about solid lifters that might not be appealing. You know, one, the noise, two, possibly, you know, the checking a lash every now and then. And I've said before, you don't need to worry about solid lifter cams going out of adjustment because, again, we're not in the dark ages. You know, we have screw-in studs now, we have chrome moly push rods, we have stainless steel valves, you know, camshaft material's better, heads are better, and nothing's moving, wearing, or bending, so nothing's going out of adjustment these days. But there's advantages and disadvantages to everything. You know, a disadvantage to a hydraulic or a solid lifter cam, one thing is the camshafts have to be broken in. You got to run the engine for 20 minutes. The very instant you start it up at about 2,000 RPM, maybe 2,500, right in there to throw oil up on the camshaft. And keep in mind, you know, the bearing journals here, these are pressure fed. These get pressure fed through the block, through oil galleries from the oil pump. The lobes, there's no pressure feeding these lobes. The only way they get oil is from the crankshaft throwing it up on there. So when you initially start up a motor, you need to run it at a certain RPM to sling the oil up onto the camshaft, or you'll have camshaft failure. I mean, for sure, you'll have a flat cam. A disadvantage, I mean, that would be a disadvantage. You have to break the cam in. Another disadvantage is you can only get so much of a profile on these lifters. And what I mean by profile is, you know, only so much lift, so much duration, etc. For a flat tappet cam. You know, the ramp speed on this isn't very fast. You know, if you see the lifter here, X amount of rotation, and the lifter rides up on the lobe. Okay, if we go to a roller cam right here, you can see these are really steep. Look at the lobe difference between this right here. It's very egg-shaped compared to this. It's almost a perfect oval. And what that does is when this lifter's riding on here, like so, this cam makes just a little bit of rotation. It's already at full lift. So, I mean, just 6 or 8 degrees of rotation, and this thing's at full lift. Where the flat tappet cams, it takes quite a bit more rotation here. You got to rotate, 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 and then go to the top. So it takes a lot more movement of this cam to get to full lift than it does for a roller cam. What that means are the valves slam open at full lift and then they slam closed. So the valves on this type of a camshaft are open longer and faster than they are in a flat tappet, and that fills the cylinders and makes more horsepower. The other advantages of roller cams, you don't need to break them in, and you don't have to worry about lifters so much. In other words, what I mean by that is on a roller camshaft, you can swap lifters around and you can reuse lifters. You can put another camshaft in and reuse a set of lifters. If they look okay, they're not worn or anything like that, you can reuse them. Well, if you take a lifter from this that was on this cam lobe here and then you move it to over here, you will wipe the cam out. So the advantages of roller cams are better lift, better filling the cylinders, making more power, faster ramp speeds, I mean lightning fast ramp speeds, not having to break it in or break the camshaft in or anything like that, and fantastic valve timing. The disadvantage, I guess, to one of these would be they're quite expensive. I mean, a decent cam for a flat tap is probably anything from $79 to $179 for a real high-end custom ground one. You get into a roller cam, especially a billet one like this that's made out of billet steel, they start at about $300, and boy, I tell you, for a custom cam, you can get right on up to $500 for a camshaft. And same with the lifters. You know, even solid lifters or hydraulic lifters, they're very inexpensive. When you get into really lightweight, high-end roller lifters, pretty expensive, $400 or $500 a set sometimes. So there are advantages and disadvantages to everything. And if you're just running a mild street motor, no sense in going hog wild like this to make 400 horsepower, and you're certainly not going to make 500, 600, 700, 800 horsepower with a flat tappet cam. So each one has its advantage and disadvantage. All right, we're talking about timing assemblies here. This right here is something typically you'd find in any factory motor. It's just a single roller set, which means it has one row of teeth right here. Of course, the top gear is the bigger gear. That's the cam gear. That's what bolts right directly to the end of the camshaft. The smaller gear here is the crankshaft gear. It goes right over the snout of the crankshaft. And of course, we have the chain. This is typical on any factory motor, like I said, but a lot of factory motors come with nylon teeth on the gears. It's not something you really want. If you're replacing yours in your factory motor and you have the option of getting nylon teeth or steel teeth like this one, go with the steel teeth. The nylon teeth tend to fall off and end up in the bottom of your oil pan. Let's go to this one right here. This is a typical double roller timing assembly. The reason we call it a double roller is because it has two rows of teeth that ride in two sets of rollers on here. It's just a lot stronger and a lot better for performance motors with higher spring rates and bigger camshafts. Now on the back of these, this is where the gear rides against the block right here. To eliminate friction on performance motors, sometimes we use what we call a roller Torrington bearing. And this is what goes on the back side here, just like that, and it just prevents wear and tear on the block. Nothing fancy about that. Now on some performance applications, people will use gear drives. This is a typical gear drive right here. It's called a dual idler gear drive. Very popular. If you like that sound, the whine sound of gear drives, this is what you want to get. Basically, instead of a chain, it just has the dual idler gears. Again, the cam gear is twice the size of the crank gear. It does the same thing as one of these, just eliminates the chain. There's kind of a wives' tale that floats around, though, that some guys, they'll say, oh, I have to have a gear drive because I'll break a timing chain. That's not really true. We use rubber belts on some race motors, on some big-time race motors. We use a belt drive, where it's actually a rubber cog tooth belt on here. And if we were breaking chains and belts, we wouldn't be using those things. This right here, though, gear drives do have their place. I mean, if you like that whine sound or that hot rod sound, these are kind of the way to go. If we look at this, though, gear drives, they don't just fit on the end of the camshaft. They have timing locators here to time the camshaft. You know, as with any timing set right here, if we look over to this one, we have timing marks. And usually you just line the marks up and go. But on performance motors, we degree the cam in. We'll get into that a little bit later. But what degreeing the cam is, we use these little buttons right here, which fit in this hole. There's a dowel pin on the end of the camshaft, and that's what comes through this hole. And because gear drives usually need to degree them in, we have these offset dowels right here with different offsets in them. Some are way off to the side and some aren't. And that can push the gear forward, the cam gear forward, or the cam gear late to advance the cam timing or retard the cam timing. We also have cam buttons right here. These are two different types of cam buttons. You use a cam button on roller camshafts. Let me show you here. They just fit right in the middle. So when the When the timing assembly is bolted onto the camshaft, the cam button rides against the inside of the timing cover. And that way the gear can't move forward and it can't go back. Because on roller cams, it's very critical that the cam stays exactly in line with the lifter. And what these cam buttons do is they prevent it from rolling forward, and of course the facing on the back of the gear prevents it from rolling back. So it just keeps the cam located. There's another type here too of cam button. This is just a solid aluminum one. And these do the same thing. They just fit right in the center just like that, hold the timing cover up, and it just holds the cam in place. And don't be surprised if you're putting one of these in that if you need to cut the back or cut the front of it to get it to fit right, because that's pretty common. It's something you can do at home though. All right, we're going to learn how to read a cam card here and what a cam card means and things like lift, duration, overlap, all that kind of stuff that you hear about cams, and learn how to understand that. When you buy a camshaft, an aftermarket camshaft or a performance camshaft, they come with what's called a cam card right here. And what that is, these are two different brands of cams and two different types of cam cards. The reason I have both of them here is just to kind of give you a comparison between one brand and another. And the cam cards are a little bit different too. One reads one from one place and one reads one from another place as far as measurement goes. So let's kind of look at this. I mean, you take the term lift. What does lift mean? Well, on the camshaft right here, what lift means, this is the base circle right here. So when a lifter's riding in this area right here, nothing's happening to the valve. As the cam rotates and a lifter rides up the lobe, that starts to lift the valve off the seat. This area right here from nothing to full lift is called lift. If we look at a cam card, we can see that right here. Here's the intake lift and exhaust lift. And neither of these go to this particular cam, but this lift right here is a 520 intake and a 540 exhaust lift. We look over here at this cam, this one would have a 525 intake and a 550 exhaust lift. Okay, that just tells you how much the valve is going to come off the seat. Now, lift has nothing to do with how radical a cam is or anything like that. It simply means, we come over here, how far the valve is coming off the seat. If it's a 400 lift cam, it means the valve comes off the seat 400 thousandths. If it's a half-inch lift, a 500 lift, it comes 500 thousandths. If it's a 600 lift cam, it goes 600 thousandths. That's all lift means. It has nothing to do with how radical a cam is. It's just the breathability of the cam and how far the valve is going to come off the seat. All right, the second thing we're going to talk about is lash. The reason we're going to talk about lash right now and what lash means is lash is the distance between the rocker arm and the valve tip. I can show you right here. When we have rocker arms on the head, the rocker arms ride right against the valve tips. Well, on hydraulic camshafts, we have no lash. It's zero lash. That's why hydraulic cams don't make any sound. But a solid lifter cam makes all kinds of sound. That's because there's a space between the rocker arm and the valve tip. That's called lash. And that's why the solid cams have that sound. It sounds like tiki valves all the time, but it's not. They have to have the lash in there. The reason we want to talk about lash right now is simple, because this right here is the cam card for a solid lifter camshaft. If we look over here, we can see where it says clearance. This is the hot lash. That's 18 thousandths on the intake and 20 thousandths on the exhaust. If the valves are set less than that, they'll be too tight. It might not close all the way when the engine's warm. If they're set too loose, you won't get the type of lift and everything out of the camshaft, and it'll be noisy. So it's important that the lash is set to the correct width, otherwise the cam won't work the way it's supposed to. Now this one over here is a hydraulic camshaft, and there is no lash. If we look right here, valve adjustment, 0, 0. That's because this is a hydraulic camshaft, so it needs 0 lash. All right, the next thing we're going to learn about on the cam card is duration and what duration means. There's different types of duration. There's advertised duration and there's duration at 50 thousandths. And the reason there is a couple of different types of duration measurements is because different cam companies measure it at different areas. Some measure it at 6 thousandths, some measure it at 15, some measure it at 20. That's why there's a 50 thousandths given measurement and then also an advertised duration. But advertised duration doesn't mean a whole lot. Let's understand what that means. Basically, duration means how long the valve is going to be off the seat in terms of crankshaft rotation. Now remember, the camshaft goes half the speed of the crank. So this is just in crankshaft rotation and degrees that they measure this. So basically what it means is how long it's off the seat. It has nothing to do with lift or anything like that. Basically, duration on a cam card is measured right here. It shows you the measurements right here. Advertised duration on this particular cam is 272 degrees on the intake and 282 degrees on the exhaust. This one right here is 288 degrees on the intake and 315 degrees on the exhaust. And one thing you might notice is these are all split profile cams, or what they call dual profile cams. A single profile cam has the same lift values. For instance, this would be a 525 lift on the intake and a 525 lift on the exhaust. And the duration would be like 272 on the intake and 272 on the exhaust. That's a single profile cam. A dual profile cam is just like this. They have different lift values and different duration values. The reason for that is the intake valve and the exhaust valve, not only are they two different sizes, they're flowing two entirely different types of gases. One's inletting a cold, wet mixture of fuel and air, and the other's letting out a bunch of hot, spent gases. So they don't do exactly the same thing. Therefore, the values on the cam cards are going to be different. So let's elaborate a little more on duration. Now, I showed you on the cam card right here the different duration values of these two different camshafts. Now, I told you advertised duration is kind of irrelevant, and that's why. See, this cam card here doesn't even tell you where it takes its advertised duration reading from, meaning at what valve lift. Is it at 0? Is it at 2,000s or 4,000s or what? You don't really know. If we look at this one over here, it says duration at 6,000s tappet lift. So this one right here gives us the value. So we can take that in consideration against other cams if they're all measured at 6,000s. The problem is they're not all measured at 6. Some are at 15, some are at 20. So advertised duration really doesn't mean a whole lot. So what we go by is duration at 50 thousandths. That's a across-the-board standard that all the cam companies use, so we can use that as a measurement between different camshafts. And if we look right here, here's one, duration at 50 thousandths intake. All right, here's the intake valve and exhaust valve. The intake valve has 240 degrees of duration, and the exhaust valve is 252 degrees of duration. That's at 50 thousandths. If we look down here, here's the same one, duration at 50 thousandths. See, again, it's an across-the-board standard that they all use. This one's 236 and 248. This is pretty standard for a performance cam. Everything below about 214 or 212 is on the lower end of performance. Anything from about 218 to 222 degrees of duration at 50 thousandths on up to 240, 250, 260, start getting into more radical cams. All right, another factor of duration is overlap. Now, what is overlap? And I'm sure you've heard that term before. You want to know what it means. And it's actually very important. What overlap is how long both valves are off the seat. Now, we talked about duration is how long the valve is off the seat. Obviously, there's two valves, and at a particular cycle in the motor, there is a point in which, in performance motors anyway, in which both valves are off the seat. In stock engines, they don't have overlap, and that's how they keep a high vacuum signal and a nice smooth idle and good low-end throttle response and stuff like that. So let me show you how overlap works in a stock engine where there is none. Okay, the piston would be at top dead center. And as it works its way down in the stroke, the intake valve opens and it draws vacuum through the intake valve. It draws fresh, cold air and fuel mixture into the cylinder. The piston comes up as the valve closes and compresses it. Then it goes bang and fires, and the piston works its way down and turns the crankshaft for you. That's your power stroke. On the way back up, the exhaust valve opens. It pushes all the spent exhaust gases out the exhaust valve. It closes. Then the piston works its way down again, and the intake valve opens. It creates a vacuum, and it starts to cycle all over again. This is called suck, squeeze, bang, blow. Okay, what that means is suck, squeeze, it goes bang, and it blows it right back out the exhaust. That's how a stock engine works. All right, now performance cams have overlap. And let's explain what overlap is. I mean, that's what makes a camshaft radical in the first place, is the overlap. Let me show you what it does right here. If this was the piston again, as it works its way down, it draws air and fuel into the cylinder. The piston comes back up and compresses it. It lights and goes bang, turns the crankshaft around. And then as it comes back up, the exhaust valve opens and it pushes all the fuel and air, the spent fuel and air, right back out the exhaust valve. Now here's where the overlap comes in. Just before the exhaust valve closes on its cycle, the intake valve starts to open. You get this area right here of overlap, okay? The more degrees of overlap you have, the more radical the engine is. And also the more degrees of overlap you have, the less vacuum signal the engine will have. I mean, a typical race cam might only have 4 or 5 inches of vacuum. A hot performance street cam might have 9, 10, 11 inches of vacuum. Whereas I said before, a stock engine might have 16, 18, 20 inches of vacuum. And that's all dictated by the overlap. And the way that works is simply because when both valves are off the seat, you can't compress or draw any air in because air is trying to travel any which way. And that's actually what gives you the rumpety idle. as it's working, the piston's working its way back up, you actually get reversion back up the intake valve right here. As the exhaust valve's open in its open cycle, and then the overlap mode as it's closing and the intake valve starts to open, it actually a mixture of fuel and air is trying to come in, but at the same time we still have pressure in here that's also working its way back up, the reversion, which lowers your idle vacuum signal and gives you the rumpity-rumpity of the camshaft. Okay, now we just talked about overlap. Now we're going to see it on the cam card and how it's measured. So we can see on this cam card right here, it says correct only at 50 thousandths tappet lift. So that tells us these are all measurements at 50 thousandths lift. So remember what I said, the overlap is when the exhaust valve closes and the intake valve opens. That's a little transition in there. So here it is, the exhaust valve closes at 14 degrees after top dead center, and the intake valve opens at 16 degrees before top dead center. And the way you can calculate the overlap on a camshaft is easy. You just take the amount here, the value here of when the exhaust valve closes and when the intake valve opens and add them together. When we add those together, we get 30 degrees. So this camshaft right here at 50 thousandths has 30 degrees of overlap. Now look at this cam card over here, they measured a little different. This is why you need to know this kind of stuff, because these are not 50 thousandths. This says valve timing, okay, right here at 6 thousandths. They don't give us any 50 thousandths on here except for the duration. So right on here we have to take the valve timing itself as when the intake valve opens and closes and when the exhaust valve opens and closes. We have to take those measurements at 6 thousandths. So that's going to give us a different number. So if we look right here, here's intake, opens, and exhaust, closes. So here's intake and exhaust, opens and closes. So the intake valve opens at 36 degrees before top dead center, and it closes at 72 degrees after bottom dead center. Okay, so again, when does the overlap occur? It occurs when the exhaust valve is on its way to close and then the intake valve starts to open. So we look on here, here's the exhaust valve closing, there's closes and the exhaust valve is 39 degrees. If we take 39 and then go to when the intake valve opens is 36, we get 75 degrees of overlap. So this cam right here has 75 degrees overlap at 6 thousandths lift. Now, like I said before, the overlap is going to dictate how rumpety the idle is. Now, some people like that. They like that sound. The problem with that sound is the more bumpety and rumpety-bumpety a camshaft is, the less bottom-end torque you get. And it might sound good to some people, but your throttle response is going to be slow. You're going to need a lot more static compression, which is, you know, the actual compression of the engine. You need to raise that up with the more overlap you have. Otherwise, the motor's going to be a slug. So you have to kind of be careful of that sound, and some people might think it sounds good, but others, when they hear how slow the throttle response is, when you stab the throttle and the car just makes a bunch of noise but doesn't go anywhere, it's usually because the cam is too big, and what they mean by big is too much overlap. All right, let's talk about one last aspect here on the cam cards. That would be lobe separation, or what people call LSA, which is lobe separation angle. Some people also call it a lobe spread. What that really means, let's look at a camshaft right here. And camshafts, the way they're laid out, because the cylinders, you know, are 4 or 5 inch bore, the lobes are not side by side. Okay, what I mean is, if this is an intake lobe for, say, cylinder 1, then the exhaust lobe for cylinder 1 is the second one over. It's not the next one, it's the second one. This might be the intake lobe for cylinder 2 on, say, a Chevrolet, and this would be the exhaust valve for the same cylinder 2. So it's, this pertains to one cylinder, this pertains to one cylinder. Okay, now what lobe separation means is the center line between one lobe and the next lobe. Like right here, as you can see, these two right here pertain to one cylinder. So this camshaft, let's say this is this cam right here, 108 degrees. That would mean that the very center of this lobe right here and the very center of this lobe right here is 108 degrees. If it was another camshaft, we can come over here. Here it is down here, lobe separation 113 degrees. That means it's a wider spread between these two here. So 108 degrees would be a narrower spread, and a wider would be 113. Now, typically, performance cams have narrower lobe separation angles. This has to do with cylinder pressures at higher RPMs and how peaky or broad the power band is going to be on the camshaft. Basically, like stock cams, they have anywhere from a 114 to a 117 spread in terms of degrees, 114 degrees to 117 degrees of spread. Whereas a performance cam might have, 110 or 112 degree spread. They bring the centers together a lot more, a lot more narrow on those. Race cams, really hardcore race cams, they're 102 degrees, 101 degrees, so they're very close. And let's look at terms on what we're talking about here, because this has to dictate with overlap. All right, so let me start with base 1 here. If the lobe separation angle was 0 degrees, that means both intake and exhaust valves are opening simultaneously. Okay, if it was 10 degrees, then it would be a slight difference between one and the other because they're only 10 degrees apart. So they're almost acting in the same. So if they're at 0, then as the camshaft turns, both valves are acting simultaneously. So as we little spread it out a little more and more and more, they start acting more independently of each other. Now put it this way, if the lobe separation angle was 180 degrees, well, there's 360 degrees in a circle. If it was 180 degrees, they would both be working completely opposite each other, just like this at all times. That's not ideal for an internal combustion engine. That's just not the way the dynamics of an engine works. So because the dynamics of the intake charge coming in and the exhaust charge going out, and with relativity to stroke and piston movement and cylinder pressures and things like that, we have to tailor a camshaft for how the engine's going to be used and for the RPM range, for how much horsepower it's going to make and what the engine's going to be used for. And by changing things like lift and duration and lobe separation angles and overlap and things like that, we can dictate on exactly how an engine's going to run, where we can make it have more bottom end power or more top end power. We can make it crispier on the throttle. We can make it laid back. Let's say an engine makes too much torque. So we can add a little bit more overlap into the cam, something like that, to where it doesn't pull as hard on the bottom end. That way we don't spin the tires coming off the line. But once we get quarter track or half track and the engines come alive, we're already hooked up and we go on down the track. Circle track cars do the same thing. Sometimes they'll lay the cam timing back on a cam, so when they come out of the corners, the engine reacts a little slower and at a higher RPM as it would if the camshaft was forward and reacting at a lower RPM. So overlap and lobe separation, that just dictates when the valves are going to be working here and how much cylinder pressure you're going to be getting. One more thing you might want to know about lobe separation is that on supercharged engines or nitrous engines, you typically want a wider lobe separation. And on naturally aspirated engines, you want a narrower lobe separation, such as this over here, a 108. That wouldn't be good for nitrous or a supercharger. But this 113 over here would be, or a 114. Also, to keep in mind, the wider the lobe separation, the less overlap you have. The narrower the lobe separation, the more overlap you have. All right, one thing I want you to know about lift is on hydraulic lifter cams, they have no lash. So the numbers you see, such as 520 and 540, that's the actual lift the valve is going to come off the valve seat. On solid lifter cams, though, this one says 525 and 550. You need to subtract the lash. So this one has 18 and 20. So we're talking 507 inch on this one and 530 on here. So you need to subtract the lash to get the correct lift numbers. All right, I'm going to show you now how to degree a cam. This right here is a 347 Ford Stroker. It's one of the motors, one of the many motors we build here at Badass Racing Engines. Actually, if you want to learn how to build something like this, be sure to check out one of our other series on Ford Strokers, and you'll be able to learn how to do this yourself. We're going to flip this over. This right here, obviously, is the timing assembly right here. And, some people can just run a timing chain just straight up, what they call straight up. And what that means, make a little pointer here. If you look at the timing marks right here, there's a little dot right there and a little dot right here. And those need to be exactly in line with the center line of the camshaft and the center line of the crankshaft. If they're off to one side or the other, then it's not in time. A lot of people just run cams like this. You don't need to degree a cam for your typical stock motor or even your low-end performance motor. When you really get into high performance stuff and custom cams and things like that, you really want to degree the cam in to make sure it's in phase with the crankshaft. And what that means is that the camshaft is in time with the crank. So they're both exactly together, not off one way or the other. They want to be both lined up so they're both rotating in unison, basically. And different cam manufacturers want different cam timing. Some might want the cam advanced, which gives you a little bit better low-end horsepower and torque. Some might want the cam retarded a little bit, which means it's, or what we call late. Sometimes we call it early and late. So advancing and make the cam early, which means we move the cam forward a little bit. The engine's rotating this way right here. It's going clockwise. So if we wanted the cam to be advanced, we would rotate it forward a little bit. If we're going to make the cam timing late, we would let the crankshaft rotate forward and hold this behind a little bit. What that would do is make a little more top-end horsepower or anything like that. So you might say, why would you want something like that? Let's say the motor makes too much torque. You can't hook up your tires to get off the line. What we can do is set the camshaft up where the timing is a little bit late, and that'll allow the torque curve to come on at a later RPM. What that'll do is allow you to get out of the hole, get that first 60 or 80 feet down the track, and then all the power comes on real strong. And that lets your tires hook up and you're out of the hole already. Sometimes in circle track racing, it's a short track. You're not running as high of an RPM that you normally would in a longer track. So you might advance the cam timing so you have a little more instantaneous throttle response and torque coming out of the corners. On a large oval track, a 3/8 mile or a half mile, you might want to run the cam timing a little bit late because you're up in the RPMs a little bit more. And this all has to do with car weight, gear ratios, torque converter stall speeds, or transmission type like a manual transmission. If you're not sure about that, call the cam manufacturer. They have techs. All cam manufacturers have techs that you can call, and they'll be glad to set you up with exactly the right cam for your application. Let's go on now to degreeing a cam and what it means and what we're doing. Here's a typical timing assembly right here, just a typical stock timing assembly. And you might ask, well, how can a cam be off? Why would we need to degree it, or how could it be off? Well, there's several factors. There's a dowel pin here that locates in the camshaft. Let's say that when they machined the camshaft and they put this dowel pin in there, that it was off 1 degree. That could happen. That's easy. What if when they were machining this gear right here, this dowel pin is off this way 1 degree? Well, that could either counteract the 1 degree in the cam, or it could add another degree to it and make it 2 degrees. What about the keyway here on the crankshaft? What if the crankshaft isn't indexed correctly? What if this keyway in the crank, this Woodruff key in the crank right here, which locates the bottom gear, what if that's off to one side or the other slightly? If that's the case, we can either compound what's off up here or subtract from it. You just never know. So the crank could be off, the keyway here on the bottom gear could be off. There's any number of 4 to 6 different places that the cam timing can be altered just because someone was off a half a degree here or 2 degrees there. I mean, let me tell you, I've seen timing sets as much as 8 degrees off, where they got this 3 or 4 degrees off and this one, and they happen to be in the opposite ways, and what happens, it throws the cam timing way off. And you think you got your cam straight up, and even though the marks are straight up, guess what? It's not. The cam's either way forward or way late. And that makes a big difference in how that motor is going to run. So in real high-end performance stuff, we want to degree the cam. We're going to go to that right now. Okay, now we're getting ready to degree the cam. First, we need to know where we're going to degree the cam at. And where we get that information from is the cam card that comes with performance camshafts. Remember, the cam card says the lift, the duration, the overlap, the valve timing, different information like that. It also tells us where to degree the cam at, where the cam manufacturer wants us to install the cam in relativeness to the crankshaft. And if you look at the very bottom of the cam card down here, it says, using the intake centerline method, we want it at 108 degrees. And that's what we're going to do. I'm going to show you how to do that. All right, well, the first thing you got to do to degree a cam is find the crankshaft top dead center on number 1 cylinder here. Of course, this is a 347 Ford that I told you earlier here. Ford's, the number 1 cylinder, is the passenger front. If it was a small block Chevy or a big block Chevy, it'd be the driver's side front. So it's a Ford, so we need to use this cylinder right here. First thing we need to do is be able to turn the crankshaft. We can do that in a number of ways. This is a crank nut right here. These are inexpensive, and basically what it does, it's got a keyway in there that slips over the snout of the crank. You can rotate it until it locks into the keyway, and you can put a big wrench on it like a large crescent, and you can turn the crankshaft. These are okay, but it's kind of a pain in the butt to mount the degree wheel. In order to mount the degree wheel, you'd have to use a nut on here and a bolt and drop it in on there. Problem is, it's kind of a pain in the butt to get it located and solid and center. So I prefer to do it a different way. I use a hub assembly right here. This is a machined hub, and it's designed for degreeing a cam in. It's got an area on the front here to lock in the degree wheel. So what this does, we just do the same thing. We lock it in. I give it a little tight right here with the Allen wrench, just to kind of lock it in place. and it just uses a regular ratchet to go on the end there, a 1/2-inch drive ratchet. Now what we need to do first is get this up to top dead center. We can do that a couple of ways. First way is with a piston stop. This is not my way of doing it. A lot of people use this. It's perfectly fine. What the piston stop does is it bolts to the deck surface of the block, and then the piston comes up. You rotate the crankshaft until the piston comes up and touches the stop. When you do that, you indicate where the degree wheel is pointing at. Then you turn the engine all the way the other way until the piston comes up and stops and touches it, and you indicate where it's reading on the degree wheel. Then by doing a little math, by dividing the two, you can get top dead center. It's kind of a pain in the butt way. I don't really like doing it that way. I prefer to use a dial indicator, a magnetic-based dial indicator. And what this does, this just locates itself right on here magnetically, and we can rotate the engine. Usually we always rotate the engine in the rotation that it's going to be turning when it's running. So we're just going to bring it right on up. And we can watch the dial indicator here until we see where it peaks out at. And right there we can see it's on its way back down. I've gone too far. So we're going to back it back up. And it really doesn't matter where this is pointing, but if you want to try and make it 0, that's fine. Bring it right on up. Just turn it ever so slightly. I'm barely moving it. And there it is right there. Okay, the next step is to install the crank gear and the cam gear. I want to show you something about this crank gear though. This is a high performance model. It's a double roller. It's got the two gear teeth right here. It also has multiple keyways, and that's for degreeing in a cam. What we can do, if you look right here, bring it right up here, 0 is 0. And what that means, if we're going to run the cam straight up, this is the one we would want to use. And if you look right here, the tooth is exactly centered above the keyway here. And then this manufacturer also allows us to advance the cam, which right here, if we look at this, the triangle on this particular brand means advance. It's 2 to 4 degrees. And if you look real close, you look at the center line here, it's not centered with the tooth. The tooth is actually forward. And what that does is it moves the gear forward, which also moves the cam forward of the crank. The crank never moved, but the gear itself moved. It rotated forward, which rotates the cam forward a little bit, which makes the cam timing a little earlier. We can also check here. This is either 2 or 4 degrees late, depending on the manufacturer of the timing assembly. Some are 2, some are 4 degrees. Some have lots more keyways. Some are in 2-degree increments, and they go all the way up to 8 degrees advanced and 8 degrees retarded. This one right here, though, you look at the center line right here and look at the tooth, it's back, which means it is rotated this way, which makes the cam timing late from the crankshaft. The whole idea here is to have the cam and the crank lined up together, or what they call in phase together. We can move the cam timing forward or late of the crankshaft, depending on what keyway we use right here. So we'll go to install this. We need to just take the hub off and slide it on. We're going to advance the cam. Some manufacturers don't grind any advance or retarding in the camshaft. What I mean by that is the dowel pin on the camshaft is located at center. Some companies, though, to give you a little more bottom end, they'll locate the dowel pin forward or they'll locate it back a little bit. What that does is when you advance the cam, you open the intake valve sooner. It gives you a little more power, lower in the RPM range. What would that be good for? Pulling out of a corner at a lower RPM faster. Let's go the opposite way. Let's retard the camshaft. If we retard the camshaft timing, it makes the power curve come on at a later RPM. That'd be good for if you got a motor that's got a little too much torque and you're having trouble launching off the line. What you can do is lay the cam back, lay the cam timing back, and the car won't launch as hard. The power band comes on a little bit later down the track, and that's when your tires have already hooked up, you're on your way down. So different cam manufacturers will advance or retard the cam timing just to the specs of what they're going to make the camshaft for you. So we're gonna find 0 on that. We'll put this one on here. We're going to go to 2 degrees advance first. And we're going to find 0 on the cam gear. I'll put this on here, locate it in, and just bring it down so the timing mark right here is centered right straight down. That gives us a location of that. And that slides back off. We can slide this on. Different manufacturers have different tolerances. Same if the crankshaft snout has been polished. Sometimes you have to tap these on with a drift punch and a light hammer or a block of wood. This one just happens to slide on just nice and snug, but I can actually move it with my fingers, and that's okay. You might run into this and you might have a tight one. It's different manufacturing tolerances. The trick is don't put it in all the way. Pull it back a little bit, because once the gear and the chain are together and going on, they need to slip in together at the same time. So we can do this. We should have our timing mark pointed straight down. We'll bring this up on here. If it was off one tooth, let me show you here. This is when it's off a tooth. You can see it's not centered. It's over here. Okay, you want to be sure that you're centered straight up and down. And there it is, right there, straight up and down. Give it a little movement there. And there we have, straight up and down. It is not quite straight up and down though, because we are using a 2-degree advanced right here, so the gear is actually forward a little bit, so the cam is actually rotated forward a little bit. All right, we'll go to the next step. All right, so the next step is to put the hub back on. This allows us to mount the degree wheel. So we're going to pop this back on. I'm going to give it a little tighten down here. This keeps it from rocking back and forth a little bit. There's always a little tolerance difference between the keyway and the hub assembly, so that's pretty tight on there. Now we can take the hub assembly off and install the degree wheel. This is your typical degree wheel right here, and what it has, you can see it's got numbers all the way around it and little areas. This shows us top dead center, bottom dead center, the intake centerline area, which is the method we're using for degreeing the camshaft. We're going to find the highest point on the intake lobe, and it's going to tell us where the degrees are in here. Remember, the cam card said we want 108 degrees, so that's what we're going to be shooting for on here, is 108 degrees. So we'll just pop this on, cinch it down. Next we need to put a pointer on. Now there are fancy-dancy pointers like these right here. These are fine. They're a little expensive. The problem is this only has a 1/4-inch thread assembly on here, which is great for a small block Chevy because they bolt right here where the timing cover goes. Problem is this is a small block Ford. It's 5/16, so this isn't any good. Next best thing to use is just a little piece of wire bent around on the backside with a bolt in it. No big deal, no brainer, a simple little thing to do. It actually works really well, and you can move it from engine to engine with different size bolts on it. The pointer is just to keep us in line with the degree wheel here. All right, and it doesn't really matter where the degree wheel's at or where the pointer's at. We can move the pointer over here, we can move it down here. We're just going to leave the pointer where it's at and move the degree wheel so it's lined up dead center of this pointer right here, which is about right there. Give that a little cinch. So now the crankshaft is right where it's supposed to be. Number 1 piston is at top dead center. We have a pointer. The next thing we need to do is something to measure where the lobe is on the camshaft. And we can do that with this device right here. This rides on the cam lobe. This is a flat tappet cam, so we're using a flat actuator right here. There are some for roller cams that also fit right inside here. You can swap these out. So this is round just like a roller. This is flat for like a flat tappet cam. So we can drop this in the intake lobe. Now on a small block Chevy, the intake lobe is the second one back, which would actually be on this side because this is number 1 cylinder on a small block Chevy. It starts with the exhaust, then the intake. This is a small block Ford, it's on this side. It starts intake, then exhaust. So we're going to take this right here and we drop it in place and it just snugs in. There's O-rings on either side of these and this drops right down in and just the friction of the O-ring holds it in place here. So we drop that in. We'll just take a wrench, pop it back in here, and we're going to see where we're at. So we're going to crank the engine over, and bring it right here, and we're just going to watch the cam lobe right here. Notice I'm going with the rotation of the motor. This is the way the motor normally rotates. So we're going to follow it right here. I'm going to bring it right on up, and we're going to see where the highest point is on here. As we can see, it's about in here, because if I keep going, it's going to start dropping back down. So let's back it up. Okay, we can bring it up to 0 in here if we want. We can try and find a point up there. The numbers on here are kind of meaningless. It's just a point of reference. If you want it to point at 0, that's fine. We can try and do that. So we'll bring it on up. There we go. It's about right in there. I can double check. Just going to see where I'm at. I'm at 108 degrees. Let's just see if we continue on, if it starts dropping down. Yep, there it is dropping down. So let's back it back up here. Let's try and find the top center again of the cam lobe. It's about right there. Yes, sir. We're at about 108, 108.5 degrees. Just about perfect. The cam card told us to be at 108 degrees. We're right on the money. That's degreeing a cam. If we wanted to make the camshaft timing late, we would move the lower gear over one notch on the keyway, and that would back the cam timing up, and we might be at 112 degrees or something like that. If we wanted to make it earlier, might be as early as 104 or 106 degrees. The cam manufacturer of this cam, though, when they made this grind for us, wanted it at 108 degrees. We're right at 108. We're right on the money. This is right where we want to be. Degreeing a cam is that simple. It's not that big of a deal once you know how to do it. All right, now we're going to talk about valve train geometry and what it is and how you check for it. Valve train geometry is very important, and a lot of people have no clue as to what it even is or how to check for it. Basically, when you're dealing with aftermarket rockers, aftermarket push rods, aftermarket camshafts and heads, and you've machined the block, all those have different variables from engine to engine. Let me give you kind of a quick explanation here. When this block was machined, let's say the deck surface was decked 10 thousandths. Well, that means this surface right here, if it was cut and trued up, that means it's 10 thousandths lower than it was. That means the head is now sitting down 10 thousandths farther. Let's say the aftermarket cam has a different base circle size, meaning the back side of the cam lobes is in a smaller diameter than the original cam. That means the lifter is going to sit down on the board deeper. Okay, all this plays part in what the geometries end up going to be in. Well, push rod length has a lot to do with it. Valve height has a lot to do with it. I mean, everything has a factor in geometry, and you can't just put a motor together, order a set of push rods, drop it in, and go, okay, everything's fine. It doesn't work that way. I'm going to show you here what it really is. This motor's already been checked, okay? This motor has already been checked, so it has a 7.800 inch push rod right here, a push rod length. So if we drop it in right here, and with the valve train geometry being correct, if we drop it on, get it setting, we look right here. I'll grab a little pointer here so we can see what we're talking about, what geometry means and what it is. If we look at the roller right here, where it's riding on the valve tip is all about the geometry, okay? Let me give you kind of a close-up here of what we're talking about. If we have a valve right here, and the rocker arm sits on here, what we're trying to achieve is that it rides in the center of the valve tip. We don't want it way off to the end right here, because if the push rod length is too long, it's going to ride out to the end. Then when the cam actuates the rocker arm and it pushes it down, it's going to roll right off the end of it, and you're going to blow the wheel right off the rocker there. If it's too far back, then it might fall back off this side when the cam's on the base circle. So it's really important that we get the correct geometry here happening, so all the events of the valve timing is working together. Let me kind of show you here. We'll get a little bit better idea on this. If I pull the push rod out, this might give you a little bit better idea. Imagine this with a very short push rod. It's going to drop down like that. Look at how far back the wheel on the roller tip on here is riding on the back of the valve tip. That's definitely not good. And if we increase the length of the push rod, watch what happens to the valve tip there. It rolls it out to the end. Now imagine if we had push rods that were too long like this. Well, when the valve opens and it pushes the rocker arm down, such as this one over here, you can see it's already pushed it way down, it would roll it right off the end there. That's definitely not good. So the object is to get the valve to ride in the correct area right there, which is just about center, maybe slightly back from center. That way, when the valve train's actuating, it stays right in the middle there, and it gives us the best overall performance and longevity out of the valve train. How do we adjust for it? Adjustable push rods. These are push rods from aftermarket companies. Comp Cams makes them, Crowder, Iskandarian, Crane, everybody makes them. Basically what these do is they screw together, and if you look, there's a little line right here, and there's a little line on the top part right here. Every revolution of this is 50 thousandths of an inch. So what we would want to do is drop one down inside here. We can open this one up. All right, in that area right there, drop it down so it sits inside. We can put a rocker arm on, and we can simply adjust the height how we want it. You can see the rocker arm moving. If I drop it down, see it rolling back, and we can roll up. As it starts to roll up here, it gets longer and longer and longer. It'll push it on up. We just want to get to a certain point where it's riding just about in the middle. Once we find that location, we can pull it out and then check the length of this. This one here says its range is from 6.8 to 7.8. Well, I already checked this engine. I know for a fact it's 7.8 inch. So if we screwed this all the way in, it would give us a measurement from 6.8 plus the distance here would bring us to 7.8. That tells us that 7.8 inches is a correct length pushrod that we need for this. A lot of people have no clue to check for this, and you really need to do that because you really damage the valve train if you don't do that. All right, one last thing you want to check for when doing valve train geometry really has to do with valve train clearance also. We're dealing with all aftermarket parts here, and there's nothing that says this particular part's going to work with that particular part. You got to check all that stuff. You can't assume anything with the high-performance parts like this. Sometimes there's interference. Rocker arms can be different thicknesses. This is a very thick one right here. Some are a lot thinner. They give you more clearances. So what you always want to do when you start out doing this stuff is just drop a rocker arm on here. I'll grab a little pointer here and show you. Just make sure there's enough distance between the spring and the rocker arm here so that nothing touches or interferes. Another thing you want to be careful of also, once you've determined your correct pushrod length to get the correct geometry, make sure that there's enough clearance from the bottom of the stud right here. There's a hex nut right here. Make sure that the rocker arm does not bottom out on that. Some instances, these are a little bit higher, and you can actually bottom the rocker arm out on that. It'll bind. Definitely don't want anything like that happen. You're just going to shave metal off, it goes in the motor, and that's not good. Things break. So just be sure that you have plenty of clearances. You can see that even the rocker arm here has been cut right in here to clear a larger spring because they know this is a lot thicker. So you just got to watch for things like that. It's real simple. Just be careful what you're doing and make sure you got ample clearance and things should be okay. All right, next on the hit list here is valve adjustments. This is real critical. A lot of people don't do this correctly and they get noisy valves or valves that don't close all the way and the motors run like crap and they wonder why. Let's look right here. Before you do anything, the first thing you need to do with aftermarket heads that have guide plates is make sure the rockers are centered over the valve tips. And what I mean by that, if we look down here, you can see these happen to be centered, but these right here are not. And what that means is the guide plate down here is not centered properly. They just sit on here. They can move from side to side like this. So when you buy a new head that happens to have guide plates on it, you can't just put rockers on it and think you're just going to go and drop it on and go, because a lot of times these aren't centered right. So what you need to do is just loosen them up a little bit, just get them where they're finger tight, and you can move the guide plate around just enough to center the rocker arm. So if we have it in here and I move it one way, we can move it one way or the other. So you just want to make sure they're centered. Once you have it centered, pull it off, give it a little cinch there. We can grab a torque wrench, bring it on down. Aluminum heads, usually 40 to 45 foot-pounds. We'll just give it a torque and a torque. Now we're centered. So now when we put the rocker arms on, we should have a good center there. One last thing you want to look for when you have pushrod guide plates is just make sure there's enough area between the pushrod and the cylinder head also. You want about 5 thousandths clearance between the actual side of the cylinder head and the pushrod itself. Even though there's guide plates, it can still touch the head. So just be careful of that, check that, and you'll be okay. All right, next here on valve adjustments, we're going to talk about adjusting hydraulic lifters. Just so you understand what's going on with a hydraulic lifter, there is a plunger inside here, and that's where the oil fills up underneath the plunger area. And I'll show you right here, it actually has movement down there. I can push it in and out. There's probably at least 3/16 of an inch of movement down there that the plunger can go up and down. Some textbooks and owner's manuals will tell you when you're building a new motor to stick hydraulic lifters in oil and let them fill up with oil. And then you look in a performance book and they'll say not to do that. Here at Badass Racing Engines, we decide to do it the dry way, where there's no oil inside. That way we know where the plunger level is going to be. And I'll show you what that is. That's what they call setting the preload. Hydraulic lifters are really easy to adjust when they're new like that and when they're empty. Basically, you want to find get the valves on the back side of the camshaft on what they call the base circle of the cam. So we're just going to turn the engine over here. We're going to watch. This is the exhaust valve. It's right in line with the exhaust port right here. Here's the exhaust port, the exhaust valve. So we're going to run this. It's opening, now it's closing. This is the overlap mode. So now this is going to close, now the intake valve is going to open. So we're just going to run that down, run it on up. There we go, now they're even. Now we're just going to give it about a quarter turn more just to be sure we're on the back side of the cam lobes, that we're not up on anything. Now hydraulic cams, they use a zero lash, which means there's always contact between the roller tip or just the tip of the rocker arm and the valve tip. They're always in contact. So we want to get what we call a zero lash. Easy way to do that, just put your fingers back here on the push rod. When it's loose, you can move it up and down and it rotates real easy. Okay, just rotate that with your fingers, tighten this nut down until you just start to feel little resistance right there. That's zero lash with no preload. Now what we want to do, you can just take a wrench. You want to try and find something like a 12 o'clock area and just give it about a half turn. About a half turn like that. And when you're done, you can lock the poly lock down right here. Give it a cinch. That's locked. Same thing with this. We can do the same thing. Run it down. We can turn the back of the push rod. Run it down right here till we just feel resistance. Put this on here. You can use just a regular wrench like this. If you want to do something a little fancier, we use these also. We can put this on right here. Give it about a half turn and lock it down. Just give it a cinch here. Done. That set the preload right there. Now some books might tell you, if you look in a performance engine building book or just a factory book, that they want 3/4 of a turn or 1 full turn. You don't really want to do that. The reason is, on a performance motor, you might have heard of anti-pump up lifters or lifters pumping up. What that means is the plunger in here, you don't want to push it down too far. If you push it down too far, what can happen is when the engine hits a high RPM and the oil pressure kicks way up, it can actually fill the lifter up beyond where it wants to be filled up, and the plunger starts working its way up. Well, as it works its way up, it increases the push rod length, which pushes the valve down farther. Now the valve can't close. It's not closed all the way. It's off the seat. So you can either run real bad because you don't have a seal in the heads, the valves aren't sealing, which are making cylinder pressure, or worse yet, they hit Mr. Piston, and Mr. Piston closes it for you, and that's an ugly situation. So with performance motors, you want very minimal, maybe between 10 and 20 thousandths of an inch of plunger depth. Some lifters, aftermarket racing lifters, hydraulic lifters, only want 6 to 10 thousandths, which is nothing. I mean, that's a quarter of a turn. That way they can't pump up because the plunger is only pushed down a little ways. It's only pushed down like 10 thousandths of an inch. So if it pumps up on accident for you, it can't really pump it up enough to open that valve too far and cause severe engine damage. We'll go on to solid lifters next. All right, so the next here is a solid lifter. Looks exactly like the hydraulic lifter, except the inside doesn't have all the hydraulic movement and the valving and the springs. It's just a little plunger inside there with a little bit of space. When we look at the solid lifter, you try and push on it, nothing pushes, it's solid. That's why they call it a solid lifter. Difference with solid lifter cams as opposed to hydraulic cams are, though, solid lifter cams have lash, which means the clearance between the valve tip and the rocker arm tip right here. That's designed into the camshaft, and different camshafts will have different lashes. Some are tight lash camshafts, which might have 12 to 16 thousandths of an inch of lash. And some of the old cams, you probably heard of the old 30-30 cams or the old Duntov cams that used to wake up the old Corvettes of the early 60s. They called those 30-30 cams because they had 30 thousandths of lash both on the intake and the exhaust. And that's a lot. That's like taking a hammer and taking a swing at a nail from here with a tight lash cam, and when you got a lot more lash, it's like taking a bigger swing with a hammer. It just beats the hell out of the valve train. And those old 30-30 cams, back in the days when we didn't have screw-in studs, we didn't have chrome moly push rods, we didn't have stainless valves, there were a lot of things we didn't have back in, way back when. The valves would go out of adjustment. Well, these days they don't do that. Once you set them, they're pretty well set. Now, a lot of the solid lifter cams, they say to set it when they're hot. Well, that's how you're going to do that with a brand new motor. I mean, you can't run the motor to get it hot if their valves aren't adjusted. So we have to take things in consideration. Aluminum expands quite a bit, about twice as much as cast iron. So what I mean by that is if this was a cast iron head, it might expand, 2 to 3 thousandths of an inch when it's at engine running temperature. Aluminum heads expand about twice that. They expand 5 to 6 thousandths of an inch. So with that expansion, it means everything lifts up and gets longer. So there's a rule of thumb when adjusting solid lifters cold. when you have aluminum heads, which most performance engines do these days, you want to subtract a 5 to 6 thousandths of an inch off the lash. So if it was, say we have right here, 20 thousandths and 22 thousandths, we'd want to go to 15 and say 16 thousandths or 17 right in there. Drop 5 or 6 thousandths of an inch off when you adjust it cold. That way when it expands, it goes right to its normal lash when the engine gets warm. So to adjust the lash, we're going to take our 15 and 16 thousandths here, and most of the time the exhaust valve has a larger lash than the intake valve. Reason being, the exhaust valve runs cherry red. I mean, it glows cherry red hot. So it's got a lot more heat on it than the intake valve. The reason for that is every time the intake valve opens, it's got cool atomized fuel and air coming in, where the exhaust valve has nothing but fire going right on past it. So there's nothing really there to cool the valve down. So we're going to take the 16 thousandths right here and go right into here, give it a little bit of lash there. We just have just where we feel a little resistance right there. We'll take our adjuster, put it in here, hold it in place, give her a spin down there, and lock it. Now the trick here, you think that's adjusted? Most people would think that. Problem is, when I tighten this, believe it or not, I stretched the stud a little bit. So you always want to go back and check, because now it's a lot looser. Okay, so what we want to do is just be careful with this. We want to back it off just a smidge, give it just a little tighter there. So you want to start off with a little bit tighter than what you would normally have. So right there we are, right there, nice. So you just want to be careful with that. We'll do the intake valve now at 15 thousandths. We'll put this in here, adjust the rocker nut right here, get it where it's at, and we know that when we cinch this poly lock down right here, that it's going to be, when it pulls on the top, it's going to stretch that stud a little bit. So we just want enough right there, give it just a little tighter where the resistance is a little more than you'd normally have. That way when we put this on here and give it a cinch, it should be just about right. Perfect. That's how to adjust solid lifters when they're cold.